My name is Sydney Meyer, and this is the lab report for the first lab in Physics 2211, section W03. In this lab, we explore the relationship between Newton's second law and constant velocity. The goal is for us to observe and measure the position and velocity of an object moving across a two-dimensional plane with zero net force acting on it. To completely analyze an object moving, we create a computer model to predict the motion based on Newton's second law and velocity concepts. By understanding Newton's second law, we are able to understand more about the kinetics of everyday motion. The law states that the rate of change of momentum is directly proportional to the sum of all forces acting on the object. So how does this apply to our lab? This law relates velocity and the net force as shown. The change in velocity is equal to the net force divided by the mass multiplied by the change in time. This means that if the net force is zero, then the initial and final velocities should be the same, meaning that the object is moving at constant velocity. This principle is illustrated below. If a ball starts moving at 5 meters per second and no force acts on it, a certain time t later, the ball should still be moving at 5 meters per second. To execute the lab and test my predictions, I took a video of a bead rolling across a flat surface in a straight line to analyze. To actually analyze the video, I used a program called Tracker to get position and velocity data by placing a point at the position of the bead per every frame. This is how we create an observational and data-based model to represent the actual motion. From there, I used a program called GlowScript to write a code that would create a model for the ideal motion of the object from the data collected in Tracker. Before explaining the collected data, I need to point out that the data is negative. This is because in the program Tracker, when setting the axes, I declared that the direction right was the positive direction. However, the object rolled to the left, meaning that the positions and velocities will be negative. I also declared that the object was moving in the x direction, which is why there is only positions and velocities in the x component of the vectors. If I were to flip the positive direction to the left, then all values would be positive. If I switch the x and y directions, then the y component of the vectors would contain the values that the x component of the vectors currently does. The magnitudes would not change. I collected data about the initial, secondary, and final times and positions to calculate the average velocity over the total motion and instantaneous velocity in the very beginning, which acts as our initial velocity. To briefly discuss how I made the model for the theoretical motion, I first changed the mass to the mass of my object in kilograms. I then changed the ball's position to the initial position from Tracker. I changed the velocity vector to the one calculated in the previous slide for initial velocity. I then changed the net force vector to 0, because this is what we are studying in this lab, is when the net force is 0 and which would assume constant motion. Lastly, I changed the velocity to be calculated with Newton's second law as shown, and the position to be calculated with the equation final position equals initial position plus the velocity multiplied by time. The while loop was also changed so that the loop would only run for the amount of time that the ball rolled across the table. The position versus time graph shown below contains the data from both Tracker, the observed, and from GlowScript, the predicted. From the graph, it is quite easy to tell that the predicted is a perfectly negative linear slope. However, the observed slope decreases slightly, meaning that the observed motion did not have constant velocity, which in turn means that there was a net force acting on the bead. Since the slope decreases, the velocity decreases, meaning there was a force acting in the positive direction. Such forces could be friction or air resistance, because both would slow the object down and cause the velocity to not be constant. Even though the predicted model assumes no net force, it is actually impossible to tell the total number of forces on the object. This is because the net force is the sum of all forces acting on the object, meaning it could be an infinite number of forces. However, it is possible to decrease the effect of some of these forces. For example, to achieve an observed motion that was closer to the predicted, I would have used a different surface like ice that is nearly frictionless to achieve constant velocity.